Good afternoon, students. Welcome to another one of my videos, our videos. This is on a new unit of ours that has to do with energy and what we call work. What you will learn to understand is the meaning of work in a physics context. There are really two big kinds of, well, I should say three big kinds of energy that we'll focus on in this unit. And well, one of them has to do with energy of things that are moving. And if we can say that if these objects both have mass m, but I say one of them moves at a speed like that, and one of them moves at a speed like that, one of them has more energy than the other. One of them has more energy associated with its motion than the other. One of them has more kinetic energy than the other. And can you guess which one it is? Of course it's this one. Objects that move faster, all other things being equal, have more energy of motion, more kinetic energy. But if we have two objects that move at the same speed v, but one of them has a large relative mass that's larger relative to another one's mass, well, then the object with more mass has more energy associated with its motion. It has more kinetic energy. And, well, an expression for kinetic energy, K, is 1/2 mv squared. Why the 1/2? Why the squared? Why isn't it just m and v? Well, there are reasons for that are going to become more clear, I hope, as we move forward. All right, but for now, get familiar. Second, now we're talking about the energy that these objects have, not because of their position, not because of their motion, but because of their position. All right, and in particular, their position relative to something else that's really important, and that is the Earth. All right, so these objects, if we take this to be some place that we're calling height 0, these two objects are located at different heights relative. Maybe we'll call this height 1, and we'll call that height 2. Relative to height 0, this object has more energy associated with its position. Or really, the better thing to say is the Earth and this object have a greater energy due to their respective positions. All right, and we call this, well, the blank's nowhere near big enough. We call this gravitational potential energy. If I said, hey, what are some kinds of energy you know? And you'd say, kinetic energy, potential energy. And I'd say, great, yeah. And then I'd say, what's kinetic energy? You'd say, energy of motion. And I'd say, yep, great. And then I'd say, what's potential energy? You'd say, stored energy. And I'd say, what do you mean? You'd say, so maybe instead of just blindly saying potential energy means stored energy, let's think of gravitational potential energy, U, G, as an energy associated with position. All right, and really importantly, we're going to dwell on this a little more. This object does not have gravitational potential energy. The object Earth system has gravitational potential energy. All right, because the whole reason that maybe this thing does have some sort of stored energy is because it's in the Earth's gravitational field. And therefore, if we let it, maybe the Earth's gravitational field could turn this energy of position into some other kind of energy and get it moving. And so it's really important to start thinking about systems of objects and what we're defining to be our system. You know, kinetic energy, this is just an object is moving, it has energy. But gravitational potential energy really is, I'll just sort of write keep your eyes peeled for things about the mass and the Earth mass system, the math Earth system. That's what has gravitational potential energy. And the higher up things are above some arbitrarily chosen height 0, the more gravitational potential energy they have. All right, but if two things are at the same, I guess I'm saying this, their bottoms are at the same height relative to some other arbitrarily chosen height 0, but this one has a larger mass than this one has. Well, the one with more mass has more gravitational potential energy. And so gravitational potential energy, UG, depends, well, on the object that's, well, in the field made by something else and how high up it is above some arbitrarily chosen 0 height. All right, so here's our thing about, we kind of capture the idea of system here, right? I mean, if I was being more specific, I might write something like M of an object, G made by Earth. So we just said two different objects, object and Earth. You won't write it as M-O-G-E. You'll just write M-G-H, but let's make sure we're okay with the idea of the gravitational potential energy of the Earth mass system. Okay, those are two definitions that you must know. Onward. Boy, these are easy. What's the kinetic energy of a 25-gram bullet? Well, moving at 350 meters per second, it's 1/2 mv squared. Now, we're going to want our masses, guess what, in kilograms. And, well, our velocity is still in meters per second. Yeah, square that and you get what you get. I'm not real concerned about it. But if you're sitting on the edge of your seat, 0.5 times 0.025 times 350 squared equals. I'm sure you know it's about 1,500. I am rounding, yes. Let's see, kilogram meters squared per second squared. Kilogram meters squared per second squared. Okay, good. An object has a mass and the speed. Object B has 4 times the mass, but the same kinetic energy. Ooh, what's B's speed? What's B's speed? Remember how we solve this sort of thing? We say something like, if we're talking about, this is about kinetic energy, but it's about speed. Well, we know this, right? mv squared. Let's write an expression for A's speed. Apparently it's 2 ke over m. And A, and sure. Now B has, let's see, the same kinetic energy, but mass 4m. So 2 ke over 4m. Well, notice that's the same as this, except for, so that's, I got this. MA, 4MA, MA. Well, you'll notice that this part, the square root of that, that's VA. So this is, what's happening? Notice this is the square root of a 4th times the original. So VB is 1/2 VA. Are you satisfied? Great. Okay, onward. Gravitational potential energy. Did I write? Oh, I did. Oh, this was going to be my year when I started doing it right, and I've already blown it. They don't want me to write KE, they want me to write K. K. All right, just write K. Don't look at that. A 25 kilogram block is lifted 1.6 meters above the floor. What's the block's GPE relative to the floor? Now, if I'm writing a good question, what is the block Earth's GPE? Yeah, you'll see it written this way. Just, if and when there's discussion of system stuff, just don't be wildly surprised. So, U, okay. Oh, this is not very hard. So this is 25 kilograms. Let's call it 10. And let's call it 1. Oh, sure. Let's see. Relative to the floor. Okay, so relative to the floor, this thing is at a height of 1.6 meters. All right, because again, apparently we're saying something like, here's the floor at height 0. When we say relative to the floor, that means let's call height 0 the floor. And now we're at 1.6 meters. All right, fine. So that's our height relative to 0. And that's 250 times 1.6. So UG, let's see, what's 6 times 250? Yeah, 400. What do we got? 400? Of course it's 400. 400 kilogram meters squared per second squared. Now check this out. What's the block's gravitational potential energy relative to the ceiling? Well, so now we've changed our height 0 to here. So this is no longer at 1.6 meters relative to this. It's now apparently at negative 0.6 meters relative to height 0 that's above this. Agreed? So now, in little section 2 of our problem, kilograms, 10 meters per second squared, negative 0.6 meters. It's 6/10, there you get 150-ish, right? Am I right, people? Right. Of course it's 150 kilogram meters squared per second squared. Oh, but it's negative. Yes, it can be negative. Negative meaning below where we've called 0. That's okay, nothing wrong with that. Okay? So, look out for these words. Relative to. Relative to means set height 0 at. How can height 0 be at the floor and at the ceiling? Well, it's not. In part A, it's at the floor. In part B, it's at the ceiling. That's okay. Okay? All right. Now, this pendulum one is a very common, what seems like tricky situation. So common, in fact, that people that have me for class very well might see this again. Yeah, so this pendulum has a length L. You can tell that it will swing down to lowest maximum height here. And we want its, well, let's say GPE. No one likes that. UG is what everyone wants to see. What is this gravitational potential energy relative to the bottom of the arc? Well, check this out. This is relative to bottom of arc means set 0 height at the bottom of the arc. Here is height 0. Here is the height that we're looking for. Oh, you may notice, look. well, remember, the length of the pendulum string thingy is L, so that's still L. And look, we've got a right triangle here. And a lot of times it's common to talk about how far a pendulum is displaced from the vertical. And so this we could call L cos theta, right? Agreed? Here's L. And this is adjacent to that angle, L cos theta. So that means if this whole thing is L, and this is L cos theta, well, remember, we want what this height is. That height is L minus L cos theta. Or, if you please. All right, that's just, that pops up. Wouldn't be the worst thing in the world if you knew how to handle that one. All right, onward. Who's making these slides up anyways? What are the units of energy? Well, K and U, of course. Remember, we have 1/2 mv squared. We have mgh. Let's see, this is kilograms. Right, there's mv squared, kilogram meters squared per second squared. This is in kilogram, well, meters per second squared for G. And then meters, oh yeah, that's also kilogram meters squared per second squared. Oh, but some of you will notice, well, yeah, mg, that's like a force. So this is just like a Newton times a meter. So that's a pretty common unit to express energies in, Newton meters. But that's given a name, all right? The Newton meter is defined to be a joule. The joule. Sure, if you want the Newton meter. Fundamentally, which in a lot of trivia questions we're interested in, is kilogram meter squared per second squared. That's the unit of energy, people. Yep. Now, who cares? Let's about just energy, but what if we want to change something's energy? Change an object's energy. Well, if there's an object here on a frictionless surface, and I want to change its energy, bear with me. So if this object is on a frictionless surface, and, well, all we do is this, it might take this object, well, it has to actually take this object from some initial speed to some final speed. It has to. There's a net force that's not zero. This thing definitely will accelerate. And, I mean, furthermore, we can actually say that the net force is ma, right? And, well, that's just F is m. Now, let's say that as this thing moves, as it transitions, let's say, from speed v naught to speed v, it moves through some displacement delta x. Well, I can actually write A in a different way from kinematics. I can write A as v squared minus v naught squared over 2 delta x. If you don't believe me, rearrange, find that equation that has all that stuff in it, and you can prove that A is equal to that stuff. Now you can start to notice that, well, look, we got a m and a divided by 2 and some v squared. So this is starting to look like, what if I did this? Take this, 1/2 m, and then Well, I got this, still got this v squared minus v naught squared over delta x. But now it's really looking like some kinetic energy sort of stuff, right? So that means if I'm careful, specifically if I do this on both sides, I get F delta X is, well, look, 1 half mv squared minus 1 half mv naught squared. I distributed that 1 half m. Well, look at this. This is K final minus K initial, F delta X. And this says that F delta X is delta K. We can change energy by applying a force over some distance. And furthermore, the change in energy is equal to the product of that force and the distance through which the force is applied. And notice also, remember what we said our units of K are? They're joules or Newton meters. Okay, okay, that's good. Let's look at a different case. Let's change this object's energy. And we're going to do that by taking the object from here to here. We're going to start it here and move it this way. And maybe, well, this is kind of like a delta H. Well, how do we do that? How do we lift this thing up vertically? Well, if we look at a free body diagram, it looks like that. At the very least, or maybe sort of on average, what we'd have to do is this. Agreed? Apply force F through that distance H, delta H. Well, so if we do this, F delta H, at least on average, in order to get from one place to another, the smallest that F could ever possibly be is mg. And so, look, that's like saying mg h minus h initial, and that's like saying mg h minus mg h initial, and that's like saying final minus initial gravitational potential energy. And once again, we have that this is a delta UG is equal to the product of a force and the distance through which that force is applied. Ah. Now here's a new one. What if we take this object, and this is not on a frictionless surface, and let's move it at a constant velocity. Well, if we move this thing at a constant velocity, we know two things. One is, we're pushing, and there must, excuse me, there must be a friction force that's equal and opposite to our applied force, right? We know that means equilibrium. Net force is 0. Well, the thing here is there's none of the up and down. There's no moving up or moving down. There's delta U is 0, and if we say constant velocity, delta K is 0. But energy does change. There is a transformation of energy that takes place here. All right, and what that is, I mean, if we say let's push this object through this distance delta x, and we push and push and push and push and push across this rough surface, well, there is this product of A and delta x. Like before, we had these products of the force and the distance through which the force was applied. The force and the distance through which the force was applied. We have that same product here, but we don't have one of these changes in energy, which was pretty neat before. We said, wow, in one case, F delta X was a delta K. In another case, F delta X was a delta U. In this case, well, energy does change. And you got to think, what happens if we push something across a not frictionless surface? Well, this will be equal to a change in some kind of energy. And the question is, what kind of energy changes? And you got to say that what would actually happen to this block? Well, a couple of things. One, because of the friction, you know what happens to the block? It heats up. It gets warmer. We say it's internal energy changes. Internal energy is proportional to a system's temperature. All right, and also, well, so we might say that we've turned maybe kinetic energy into internal energy. Or you know what else happens when this thing? You know what else happens? Can you hear that? Well, we've turned some kinetic energy into sound energy. Okay, so applying a force through some distance in some cases can change kinetic energy, in some cases can change gravitational potential energy. In some cases, neither one of those change, but there are energy transformations that take place, and that might be, you know, that we change one of those. You're really only going to ever see this in questions, but this clearly happens when things rub against each other, friction. All right, there's a thing like this. Let's speed this bad boy up. Again, not frictionless. It means we're going to have something like this. If this is going to speed up, we get a bigger applied force than a friction force. Well, you know what? I'm just going to say that that's the same thing as this. Agree? Where the net force is A minus F. Well, remember, if we go net force equals MA, remember what we did with this before? This MA, we said that's M V naught, V squared minus V naught squared over 2 delta X. And then we ended up taking this delta X and moving it over here. Net force delta X is, well, here's the 1/2 M. Here's these guys, V squared minus V naught squared. Net force times X is, well, I'll just write that again like that. Or delta X. So what you notice, what you need to notice is we keep seeing something about energy changing and a product of force and distance. The question is what force? You know, in this case, the net force. In this case, a vertical force. In this case, a horizontal force. In this case, a single force. In this case, kind of two forces. In this case, two forces. In this case, two forces. So there's a bunch of different considerations with force, but the idea is any and every time you see this, a change in energy, and you see this, the product of force and displacement, recall that is the definition of work. All right? So definition of work from a physics standpoint is F times delta X. And that's going to, well, in some cases, in every case, change energy. Work changes energy. All right? And a couple of things to sort of be aware of. You know, we said, like, at least in one case, for any single force, for any single force. The work done by that force is the force times delta x, sure. For any combination of forces, we say that the net work, or work done by the net force is the net force times delta x. And what we just saw from that is the net force is is equivalent to change in kinetic energy. That's called the work. This is called the work kinetic energy theorem. Work kinetic energy theorem. All right, a single force that acts through some displacement, well, take that product, that's the work done. And that's got to change some sort of energy. Are we lifting something up? Well, maybe it equals, maybe that's equal to delta U. Maybe it's equal to delta K. Maybe it's equal to delta internal energy. Sometimes we call that delta Q. Yeah, delta U, really. I'll leave that. Never mind. Don't worry about that, what variable we use. Okay? So now, notice that since work is F times X, work is measured in Newton meters, work is also measured in joules, because work is, by definition, the process through which energy changes. All right? A little thing to keep track of also is if we have the following situation, this force acts through this distance. Yeah, it's not going to do what I want it to do. Sure it will. Group. So we pull. Uh-oh. We keep pulling like that. Well, notice this force isn't entirely responsible for this motion. And, well, the bottom line is this component of the force is. Right? A force does work if that force is directly responsible for an object's motion. And so, the component of the force that does work is the component of the force that's parallel to delta x. So, big deal, we really have to say that work done by a force is F parallel times delta x. Or many times you'll see it that if there's an angle like that, that means we are F cos theta times delta x, or you'll see it lots of times as F delta x, or just x cos theta. But here's what I really recommend you sort of try to deal with. Because then we don't have to, let's not wed ourselves to W-E-D. Let's not wed ourselves to a trig function. Let's just make sure we're always talking about the component of a force that's parallel to a displacement. Okay. That's an intro into energy and work. See you soon, children and others.